All right, so this is where we left off last time, so this is where we're starting today. We got through all the different types of bonds last time. We got through things like what's an ion, what is an ion. Yep, and so it's going to either have a positive or negative charge because it either lost or gained an electron. If it has gained an electron, what do we call it? It is negative, and we give it a name. An ion. We also looked at the different types of bonds, like ionic bonds, which was on your quiz today. What was a covalent bond? Yeah, they share the electrons. What else did we go over? Things we find inside the nucleus. What do you find inside the nucleus of an atom? Protons and neutrons. What do you find on the outside then? The electrons circle around. As far as need to get. Now, we're going to get away, I was going to say, it is kind of in the whole chemistry realm, but it's not complete chemistry. He's looking at different types or classes of compounds. There are some compounds that are called inorganic. There are some compounds called organic. What's the basic difference between them? Yeah, organic compounds contain carbon. Inorganic compounds do not contain carbon. So some examples of inorganic compounds. Water. What's the formula for water? H2O. Any carbon in there? No. Salt. What's your basic table salt? NaCl. Any carbon in there? No. And so it also includes most of the acids and the bases. Like hydrochloric acid, there's no carbon in there. They do not contain carbon. Organic compounds, yes, these are the ones that all contain carbon. They're usually a whole lot larger. They usually have covalent bonds, a little bit stronger bond to hold them all together. And our four basic classifications of organic compounds: carbohydrates, which we'll talk about today, fats, which we'll talk about today, proteins, which we'll talk about today, and nucleic acids, which we'll talk about today. We're going to focus mostly on the organic compounds today. Now, any guess where you find nucleic acids? DNA. What does DNA stand for? I got acid. Deoxyribonucleic acid is where you're going to find nucleic acids. Both are equally essential for life. You cannot live without water and salts. You can't live without carbohydrates, fats, proteins, or DNA. And I'm like, so we need both of them. Now, we're going to focus a whole bunch on organic compounds today, but we're going to look at one particular inorganic compound first. The biggest one that you're going to find inside the body is water. It is the most abundant inorganic compound out there. When they say you're mostly made up of water, it's true. You are mostly made up of water. 60 to 80% volume of our living cells is all water. Most of the fluids in our body, all water-based. So it becomes the most important inorganic compound in our body because it has lots of different properties. Other than the fact you just find lots of it, that's not, that's important. You are mostly made up of water, but that's not all the cool stuff that water can do. Water has lots of different properties that make it very important in our body. Some of the different properties of water. One, it has a high heat capacity, which means it does not like to change temperature. It can absorb and release heat with very little temperature change. You can go outside, and imagine you walked in, outside and it was 120 degrees. There are things in our body that are going to, keep us at the same temperature, but in general, your cells are not all of a sudden going to turn to 120 degrees. Your skin temperature is not all of a sudden going to instantly turn to 120 degrees. And it's kind of the same reason why people that live along the ocean, that water stays relatively the same temperature, even if it's 100 degrees outside in the summer, that water temperature is still 55 degrees. Even in the middle of winter, if it's 0 degrees outside, that water temperature is still about 55 degrees. Water does not like to change temperature. So it prevents sudden changes in temperature. Why is that a good thing, to prevent sudden changes in temperature in our body? Yeah, we need to stay the same. And otherwise, cells could start burning up or freezing, and it would not be good. So we try to stay about the same temperature, and water helps do that. It also has a high heat of vaporization, which means it requires large amounts of heat, and then water starts to evaporate. It starts to go from liquid to gas. We call this evaporation, and we use this for cooling. This is the purpose of sweating. Sweat is mostly water-based. Or it's mostly water. It is water-based. And it requires large amounts of heat for that evaporation to happen, which means you're not just, if you go outside and it's really, really cold, you don't have lots of evaporation happening. Otherwise, we'd be dehydrated all day long. It requires large amounts of heat, and generally as you get hotter, it becomes hot enough for evaporation to happen, and you cool off. Also, it has some polar solvent properties, which means if you put different things inside of water, and we'll talk about ionic substances and how this happens a little bit, polar substances, such as ionic substances, will dissolve and dissociate into their ions. The example, sodium chloride. If I put salt in water and you mix it up, do you see little salt crystals anymore? No, it dissociates and it separates into sodium and chloride. They're no longer connected anymore. They dissociate. And I'm like, water has that effect. Water likes to break apart ionic substances. Now, an ionic substance means what? It will have a partial charge once it's split. When they're together, what type of bond do they have? An ionic bond. And so it's going to break apart any type of ionic bond into its ions. So sodium chloride is stuck together using an ionic bond, and when we break apart, sodium has a plus symbol, chloride has a negative symbol because one's gained one, one's lost an electron, or one has an extra one, one's missing one. And so water likes to break apart ionic substances into their ions. And so it makes it the body's major transport medium. If an ion needs to get from one part of the body to the other, like it can dissolve in water and transport around that way. You guys like my cartoon though? Thought it was funny. There's so many more chemistry cartoons. You'll probably see more in this, in this one PowerPoint than anything else, than any other thing. I'm like, I almost wish I could teach chemistry just for the little comic cartoons that you can find. And this was the book's demonstration of, yes, if I put a salt cube in water, eventually those little water molecules that look like a little Mickey Mouse at your heads, these are going to break apart and hold on to sodium. A whole bunch of them are going to break apart the chloride, and they've split. It was sodium chloride stuck together, and now breaks it apart into its ions, the sodium and chloride by itself. Other things about water. One, it has some reactivity. Anytime you have different types of chemical reactions, whether we're building something up, whether we're breaking something down, water always seems to be a big part of it. Now, I actually could have a couple other prefixes, suffixes in here, because I'm going to write other stuff on the board. Now, it's a necessary part of something known as hydrolysis. I'm going to write another one on here. Anything hydro, what do you think has to do with? Water. Just like hydrate has to do with water, hydro has to deal with water. Lysis, because you're going to see it in lots of PowerPoints, and I'll write it up then. The word lysis, anyone have an idea? Yeah, breaking apart. I got one more because it's on here. Anyone know if you put DE at the front of something what it means?
Taking the water out.
Yeah, DE means removing. So we need water as a part of any type of hydrolysis type of reaction. Now the word hydrolysis, if you break it down, what does hydrolysis mean? Water breaking down. Look at this. I've got this big, huge molecule that's made up of 4 strung together, whatever it is. Water can come in, and it can break that molecule down. Now I have just 3 over here, and I have 1 all by itself. At the ends of big, long molecules, they usually have an OH on one side and an H on the other side. And an H plus an OH equals H2O, water. And so I'm like, water can come in and break it down. So now I've got one of the H's for my H2O, and here's another H and an O, and it breaks it down. So I still have an H and an OH on the ends of this molecule, and I still have an H and an OH on the ends of this molecule. It's just using water to break molecules down. That's hydrolysis, using water to break things down. The opposite then, we have dehydration synthesis. Based on the name, dehydration means removing water. I'm like, if you're dehydrated, it is you've lost lots of water. You removed a lot. Now I have two different molecules. One has two little green circles, and the other one has one. If I remove this water, those two molecules get stuck together, and I have now made something. That's what the word synthesis means. So I have dehydration synthesis. I removed water to make this larger molecule. And so we can use water, adding water to break things down, removing water to build things up. So I can break things down, build things up. We do it all the time in our body. We're making things, we're breaking things. And then we also have, not related to that part, we use water in our body as cushioning. We've got fluids surrounding different body parts. Again, those are going to be fluids that are going to be water-based. It protects organs from physical trauma. Cerebrospinal fluid is protecting what? The spinal cord and the brain. We have cerebrospinal fluid all over our brain. So when you bump your head against a wall, hopefully you shouldn't do any serious damage to it. So there is cushioning there. Again, water-based. Now, salts. We must say it's our last inorganic thing. It's an inorganic compound. It's an ionic compound. We've already kind of briefly talked about it because of what water does to it. Because if you put a salt in water, it will dissociate into its ions. Now, there are more than just sodium chloride out there as a salt. It's the very common salt, so it's usually the one we talk about. There are other salts in the body. Sodium chloride is the biggest one. Calcium carbonate is another salt that if I put calcium carbonate into water, it will break apart. Potassium chloride and other calcium phosphates. These are salts. So what a salt is, you can give me an example of one, and I'm like, but what a salt is, it's something that when I put it into water, it's going to break apart. It's going to break down into ions. Now, what's cool about when I, put the salt in, the ions that now are floating around all by themselves, these ions are called electrolytes, and they can conduct electrical currents. So if I put sodium chloride into some water and I mixed it all up and it all broke down, the water broke apart it down, so now I've got sodium chlorides floating all around in the water, I can put a little electricity to it and it's going to conduct electricity. Those ions are going to be able to bounce electrical currents through that. Not all ionic compounds can do that if you put them in. Some will break down, but what ions are there are not going to conduct electrical impulses. So the ions that are broken down are called electrolytes, and they conduct electrical currents. Now, where have you heard of electrolytes before? Sports drinks. And when they talk about the electrolytes that are in your sports drinks, what do they really mean? They mean salt. I was going to say, a couple of you have them. And I'm like, it's salt. If you ever look at, your Powerade, they generally are talking about there's salt in your Powerade or your Gatorade or whatever else. And because, again, salt water doesn't taste good, they add what to it? Sugar. So it tastes like sugary salt water. Yay. That's what you're drinking. You were storing electrolytes. You were storing salts. And I'm like, or generally your sodium that you've lost throughout the sweat. Now, the interesting parts in salt, and I'm like, these sodium and chloride, when they dissociate, conduct electricity, it becomes very, very important. If you ever live near an ocean where there is lots of salt water conducts electricity more than, say, the river water. So if you'd be living by an ocean and a thunderstorm comes around, should you be swimming around in the ocean? No, because I'm like, it could all of a sudden have a lightning bolt that strikes like a mile away. That electricity can still get all the way to you. And like if it struck a mile away in the Mississippi River, you're probably fine. It's not going to get all the way to you a mile downriver. In an ocean, it can travel very, very far because that electrical current can go through all that the sodium ions that are in the water. So don't swim in the ocean if there's a thunderstorm. A little life-saving tip there. The ions, again, they get broken down when we put them into water. Depending on which ions that they're breaking down, there's so many different functions that they serve. We're going to talk a ton about sodium, a bunch about potassium, a bunch about calcium, a little bit about iron throughout the semester. These ions, when broken down, serve lots of functions. Because generally, sodium ion by itself is very reactive, and it can be very explosive if you'd ever add it to water by itself. You have to add it with the sodium chloride and let the water bind to it. These ionic balances are vital for homeostasis. We have to have so much sodium in our body. Like we have to have so much potassium in our body. Otherwise, certain cells are not working correctly. Now, I was like, some of the salts, they do contain cations other than hydrogen and anions other than OH, because we're going to talk about H and OH coming up. When we talk about salts, I'm like, you're generally not going to see anything that ends in OH, and you're not going to see anything that has an H in it. I was going to say H and OH, they can separate into H's and OH's in water. We don't generally call them salt. I'm like, and guess what we call them when you've got lots of H's or OH's? Acids and bases, which we have coming up. There we go. Acids and bases. Yes, they do break down in water. We don't call them salts, though. We call these acids and bases. If you are an acid, you are a proton donor. Now, again, what can you tell me about a proton? Yep, and? That's a positive charge. Now, this always confuses everyone, because you're like, why are we talking about protons? Acids are something that release hydrogen ions in solution. What charge does hydrogen have? Positive. So we're calling our hydrogen ion, because it has a positive charge, a proton donor. That's our proton, is that hydrogen ion. So anytime you see something that has lots and lots of hydrogen ions, you have H's, it's always going to be an acid. Always going to be an acid. When we talk about through the rest of the semester, if I talk about, this has hydrogens in it, acid or base? Acid. And I'm like, anything hydrogen related, acids. Because if you've got lots of hydrogen, you're considered an acid. An example, hydrochloric acid has hydrogen ions, and then it has chloride as well. Bases are proton acceptors, so the things that want those hydrogen ions. So they take the hydrogen ions, or they uptake them from solutions. They're the ones that try to find hydrogen ions, and they'll bind together. Now, acids have lots of hydrogen ions. Bases have lots of hydroxide ions. It's these hydroxide ions, here's my little hydrogen, that accepts a hydrogen ion. And if an OH joins up with an H, it becomes H2O. It's going to become neutral. So if you mix an acid and you mix a base together, if you mix an acid and you mix a base together, it should neutralize. The hydrogen part of it and the OH part of it are going to join together and become water, which has a pH of 7, neutral. And so the OH part of bases, will it accept that hydrogen proton? It'll accept that hydrogen ion. The OH plus the H becomes H2O and becomes neutral. So bases have lots of OHs. They have lots of hydroxide ions. And they want to try to find lots of hydrogen ions, which are what the acids have. I was going to say, oh, I had another one. So when we measure hydrogen, or when we measure pH, again, the pH is the potential of hydrogen. We're really looking at how many hydrogen ions something has. That's the pH scale, is how many hydrogens does it have. If it doesn't have a lot of hydrogens, it's probably going to be a base. If it has lots of hydrogens, it'll be more acidic. So as the number of hydrogen ions increase, so the more hydrogen ions you have, the acidity increases. It becomes a stronger acid. Now, since we're looking at a hydrogen ion, hydroxide ion balance, if you get more hydrogen ions, what's that going to do to the amount of hydroxide ions? They always go offset. It goes down. It's like you can only have so many of something. And it's like if you get more hydrogen ions, your hydroxide ion number goes down. So as your hydrogen ion increases, you have less hydroxide ions. You're a stronger acid. The stronger acid you have, the more hydrogen ions, the less hydroxide ions, and your pH decreases. The number goes down on the pH scale. Now my little note, this always confuses people. It doesn't matter how many classes you've taken with pH, and you've learned about pH in like every class you ever take. It still confuses people when you talk about a stronger acid means what when it comes to number? A smaller number. And that still confuses a lot of people. The stronger the acid, the smaller the number. And so when I talk about a pH decreases, and you're like, oh, it gets smaller. You're right, it does get smaller, but it gets stronger. The smaller the number, the stronger the acid. And so the more hydrogen ions you have, the pH decreases, the stronger the acid. Again, people are like, oh, it decreases. It's less strong. It's not. It's stronger. And then the opposite. As you have less hydrogen ions, you start to have more hydroxide ions, and they can flip going the other way. Your pH increases, and it becomes alkaline. And guess what the word alkaline means? It means it's a base. Instead of always saying it becomes basic, we'll use the word it becomes alkaline. Because if I start going around saying the word, it becomes basic, and everyone's like, oh, it becomes simple? No. And I'm like, it means the same thing. Something that becomes basic, high pH, this is another word for alkaline. I'm like, it's easier just for me to say alkaline, and it makes more sense when you're listening to it or reading through it. So the alkalinity, the more basic it becomes. So it's just this offset of hydrogen ions and hydroxide ions. The more hydrogen ions, the more acidic. You're going to have less hydroxide ions. And if we flip it, the less hydrogen ions you have, the more hydroxide ions you have. Now you've become basic or alkaline, and your pH goes up at the top end of the scale. What does the pH scale go from into? 0 to 14. And so neutral is 7, right in the middle. That's going to be your, pure water. Now when we get down to these low pHs, again, the lower the number, the stronger the acid. So like pH of 1 or even pH of 0, there's different types of molarities of hydrochloric acid. Very strong acid. The smaller the number, the stronger the acid. Lemon juice or gastric juice. Where do you find gastric juice? In your stomach. Very low pH. It can break down just, lots and lots of stuff that gets there. The coffee that you're drinking right now, also slightly acidic, not super strong acid. And then again, we go all the way up to some different examples of things that have a higher pH. This is showing you the reversal of the hydrogen and hydroxide. The column on the right is hydrogen, the column on the left is hydroxide. Now everything's to the negative scale. I just want you to look at the numbers. Mike, as this number starts to go, I was going to say down, up, and I'm like, we're looking at negative. I'm like, it reverses with the other scale. And so I'm like, as you start to get more hydrogens, you get less hydroxide, and it reverses. Now, when we look at pH numbers, this is all to the 10th difference for every pH, which means if you have something that has a pH of 2, and I compare it to something that has a pH of 3, this is a 10-fold difference in hydrogen ions, which means this pH of 2 has 10 times more hydrogen ions than something that has a pH of 3. Because the more acidic, the more hydrogen ions. It has 10 times more hydrogen ions for every one pH change. If I compare the same lemon juice that has a pH of 2 to something that has a pH of 4, any guess how many more hydrogen ions this has? Not 20. 100. It's like 10 times 10. And so it's now 100-fold. So your lemon juice has 100 times more hydrogen. If I compare it to your coffee, which is a pH of 5, it has 1,000 times more hydrogen ions. So it's always a 10-fold. It's, lots and lots. It's a huge difference in numbers of hydrogen ions as you go throughout the pH scale. Now, why do we care about all the acids and bases? Well, we need to maintain homeostasis, and so we need to maintain our acid-base balances in our body. Any pH change interferes with cell function and can damage living tissue. So any type of little pH change, anytime it gets a little too alkaline, a little too acidic, that can change how things work in our body. Even a slight change in pH can be fatal. And this is why I'm like, our urinary system is one of the biggest things that helps keep pH the same. This is why people that have kidney disease, if they don't undergo dialysis, will die. And I'm like, because we can't get rid of extra hydrogen ions or extra hydroxide ions. And I'm like, so even just the slightest bit of pH change can be fatal. Now, pH is regulated by the kidneys. It's also regulated by our lungs. We'll talk more about when we get respiratory. And there are different chemical buffers that try to help resist any change in our body when it comes to pH. An example of a very narrow pH in our body that has to stay the same, our blood's pH range, you know this from Fundies, is 7.35 to 7.45. Very narrow range of blood pH. If it varies anywhere above that, tissues start to become damaged. And it doesn't take much for all of a sudden you start to become damaging tissues, whether it becomes a little too alkaline, a little too acidic. Now, onto our organic compounds. So these are all the things that contain carbon. Exceptions to that rule, carbon dioxide and carbon monoxide, although they do contain carbon, we consider them inorganic compounds. I'm like, these are going to be in gas form, carbon monoxide and carbon dioxide, we consider them inorganic. So it's kind of the exception to the rule. Otherwise, our 4 basic classifications, we already mentioned it, that are big organic compounds, carbohydrates, lipids, proteins, and nucleic acids, which we're going to look at right now, starting with the first one, carbohydrates. And you've all heard about carbs and carbohydrates, you know, all over the news and different diet things like that. These are your sugars, these are your starches. Now, based on the name, carbohydrate, Mike, it has carbon, and it has hydrogen, and it has oxygen. It only has these 3 different elements in a carbohydrate. Now, based on the word, carbohydrate, what does carbo mean? Carbon, so we know it as a carbon. What does the word hydrate mean? Water. H2O. Carbohydrates always are in a ratio, of 1 carbon to 2 hydrogen to 1 oxygen. That's why my little n is after that. I can put any number in there. It's a carbohydrate, as long as it always has a ratio of 1 carbon to 2 hydrogen to 1 oxygen. The basic, they call it the empirical formula. The basic formula is always carbon, H2O, carbohydrate. Makes sense now? Example of a carbohydrate. First, what carbohydrate is that? It's glucose. Is it in the ratio of 1 to 2 to 1? You betcha. I just stuck a 6 in that end place, and I have 6 carbon to 12 hydrogen to 6 oxygen. It's still in that same ratio of 1 to 2 to 1. And I'm like, it's a carbohydrate. It will always have that same ratio. Now, in that ratio, we can change how those carbons and hydrogens and oxygens are all, mixed around and stuck together and, structured. They all have the basic formula, but they can be structured different. And we separate our carbohydrates into 3 classes. Super easy. Monosaccharides, 1 sugars. Disaccharides, these have 2 sugars stuck together. And polysaccharides has many sugars stuck together. Because what does saccharide mean? Sugar. You guys are so brilliant. Now the functions of our carbohydrates. 2 major functions. The most talked about one, it's the major source of fuel, of our cellular fuel. For our cells to do their job, they need an energy source. That's your carbohydrates. We break things down. Carbohydrates can be super big, huge, complex structures. Generally, they're all based on sugars. A polysaccharide, I'm like, these are your really complex starches. Just means lots of sugars all stuck together. It's your basic energy source. It's your basic cellular fuel. We also find carbohydrates as structural materials. In RNA, the sugar you find in RNA is known as ribose. Do you remember what the sugar is called in DNA? Deoxyribose. We just add the deoxy in front of it. And so some of these sugars can be structural molecules as well, such as the ones found in DNA and RNA. Biggest function, energy source. Lipids also contain carbon, hydrogen, and oxygen, like carbohydrates. Not always in the same ratio. We can't have a nice little cool little formula. Some lipids contain phosphorus, not all of them. Some unique things about lipids, it's insoluble in water. Can you mix a fat and a water together? No, they always separate. That's when you mix oil and water, and if you've got certain salad dressings, the oil sits on the top, the watery part sits on the bottom, you got to mix it up together, and it still doesn't actually mix up, but it mixes up enough you can put it on your salad and eat it really quick. But they're insoluble in water. It's the easiest distinguishing characteristic of all lipids. Now, there are different types of lipids. One are neutral fats or triglycerides, which we'll talk about. These are kind of like the fats that you eat. Phospholipids, where have you heard of them before? Yeah, the cell bilayer. So we're not going to actually talk about phospholipids today. We're going to talk about those when we get into the cell next time. And steroids. And these are going to include even some of the hormones that we get from like testosterone. Steroids are going to be, these are your lipids. I'm like, they're all going to have some of the basic structural formula and makeup and how they're organized. They're lipids. They're not soluble in water. Now our neutral fats are our triglycerides. They're called fats when they're solid, and we call them oils when they're liquids. So if you ever look at something you buy off the shelf, and I'm like, anything that's an oil, and I'm like, it's going to be in liquid form, it's a liquid fat. And if it's solid, we just call it a straight fat. Now, all fats or triglycerides have a glycerol molecule. It's a 3-carbon glycerol molecule. And attached to it, now do you remember how many things can carbon bind to? 4. If you remember last time, if it was a long time ago. Carbon has 4 electrons in its outer shell, and how many does it want? It wants 8. And so it either wants to get rid of 4, it wants to, take 4, or it can share 4. So I'm like, it's a very versatile thing, which is why anytime on here, you're always going to see carbon with 4 lines coming off of it. And I'm like, and we don't even draw all of the lines, so it doesn't look so complicated. We just say an H2, so there's 2 lines, plus there's 2 hydrogens there, 4 things. Now, there's a 3-carbon glycerol molecule in a fat, and attached to that 3-carbon glycerol, there are 3 fatty acids attached to each carbon. Now, these 3 fatty acids are going to come important on my next slide, but there's always 3 fatty acid chains that hang off of a glycerol molecule. That's your basic formula for a fat. Now, different functions of it, energy storage. We've got lots of energy in all the bonds in here. Insulation keeps you warmer. And for protection, if you get bumped, you've got a little fat layer there. Now, have you heard of saturated and unsaturated fats? Now, any guess what the word saturated means? It means full. If you are saturated, you are full, which means a saturated fatty acid has the maximum number of hydrogen atoms that it can have. Like, you can't put another hydrogen atom anywhere else in there. I'm going to draw this out, although there's a picture in your book too. So if I look back at this, this means every carbon that's here is completely full. And I'm like, you can't have any more than 2 hydrogens on any of these carbons. They're full. At the very end, you can have 3. It's full. It would be a saturated fat. Every single carbon that's on here is totally maxed out with hydrogens. You can't shove another hydrogen anywhere else in there. That's your saturated fatty acid. An unsaturated acid means it's not full. It doesn't have all the hydrogen atoms that it could. It's missing a couple. Now, I've got pictures of unsaturated and saturated fats up there. And then guess what the difference between an unsaturated and a saturated fat, other than based on the name full and not full? The saturated are not as good for you. How do you know the difference if you go to the store? Besides reading labels? Solid versus liquid. And I'm like, a saturated fatty acid, again, its chains, and I'm like, this is an example of a saturated fatty acid. I'm going to draw a not as pretty picture. So if you've got 3 carbons, there's your 3-carbon glycerol. All the hydrogens, all the carbons that come off of it are totally full. There you go. They form straight chains. This is my ditto. They form straight chains. If I drew a shape around this, what shape would it be? It would be a square, kind of. More rectangular. Saturated fat. However, if you have an unsaturated fat, which means I might not have 2 hydrogens here. So I've got my 3-carbon chain. Now I only have 1 carbon, or 1 hydrogen stuck to that. However, carbon still has to be bonded to 4 different things. Any guess what it can do? It can double bond to the next carbon, which also will have to be missing a hydrogen. Anytime you see carbons double bond, it changes their shape. and they bond at an angle. And then it continues up here with the CH3. And then these can be the same. Can I draw a shape, a nice perfect shape around this? No. I draw it, it ends up like that. A saturated fat. And I'm like, nice 3 straight lines. I can draw a little rectangle around it, like a brick. Do bricks stack up nicely with each other? You betcha, that's why we use them to build. They stack up nice and tight. It forms a solid. Liquids, are these going to form up nice and tight next to each other? No, there's going to be space in between these, because if you got these little things sticking off the top, and I'm like, they're not going to form nice and tight bonds and stick next to each other. They form into a liquid. I'm like, because they're not all nicely stuck together. That's what happens in an unsaturated fat. So if you go to the store, I'm like, all the oils that you would see, in the oil aisle, those are all unsaturated fats. They don't have all the hydrogen atoms they did. However, now you can take oil, we're going to make margarine here. You can take oil, which is based, or margarine, which is based on oil. However, is your margarine liquid? No. And I guess what they did to it? They added something. They added hydrogens to it. And so they took an oil and they, in a lab, added hydrogens to that oil to make it more of a solid. So you can spread that oil now on your thing. This is when they talk about, if you ever read the back of something, it'll say partially hydrogenated oil. What do you think hydrogenated means? Added hydrogen to it. And so all it is an oil that they added hydrogen to it, and it becomes thicker. Yeah, it makes it less healthy than unsaturated. Yep.
So why use it over butter? I mean,
it's still supposed to be better. It still has less hydrogens than a full saturated butter would. But yes, it's, not as healthy. And it's made in a lab and it's manufactured and not natural whatsoever. I still use it. Only because I'm like, it's easier spread. Butter out of the refrigerator is like a rock. And I'm like, margarine out of the refrigerator is still soft. And so it's not quite fully saturated, but it's more saturated than it was in oil. All right. On to another fat, steroids. The most important steroid that we'll talk about in this class, I'm like, is cholesterol. Cholesterol is a steroid. It is a fat, it is a lipid. We find cholesterol in our cell membranes. You'll see this coming up when we talk about cells. Cholesterol is important in making vitamin D. There are various steroid hormones associated to cholesterol, like testosterone and estrogen. So people that have cholesterol levels that are off generally have other steroid hormones like testosterone and estrogen levels off as well. And it also helps make bile salts that helps break down fats, which we'll get more into when we get into the digestive system. So it's an important steroid, but cholesterol itself is a lipid. Another big organic compound are proteins. I'm going to have to erase stuff. Now, proteins have carbon, hydrogen, oxygen, nitrogen. There's your tron. And sometimes it has some sulfur, sometimes it has its phosphorus, just depending on which amino acid that you find in that protein. Proteins are made up of amino acids. There are 20 different amino acids out there. That's it, just 20 different amino acids. And every protein is just made up of a different combination and different number of these 20 different amino acids. So amino acids are known as monomers. What does mono mean? One. And so one amino acid, and I'm not going to draw all the structures out. Here is my one amino acid. It's my circle. That's a monomer. If I stick it to another amino acid, and I guess what that now becomes? A polymer. Well, it did become a dimer. We're going to add another one to it. 3 of them. We call this now a polymer. Now, because we just don't call these polymers. Amino acid by itself is an amino acid. When we string a bunch of them together, because this isn't on your notes, we call this a polypeptide. Poly meaning many. Peptide has anything to do with proteins and amino acids. So when we string a bunch of amino acids together, we call it a polypeptide. No. It is an example of a polymer. But polymer just means many of whatever you stick together. So a chain of amino acids is a polypeptide. However, a polypeptide is not quite yet a protein. Just a long chain of amino acids, which is a polypeptide, is not a protein. A protein is taking that polypeptide and folding it and twisting it into a very specific little shape. Then it's now considered a protein. Polypeptide is just a chain of amino acids. And I'm like, once we fold them up into a very specific shape and they get folded in a very specific way, then they can do their job, whatever it is. Then it becomes an actual protein. Now, what connects one amino acid to the next is a peptide bond. I'm not going to go into all the structures of it. But again, anything that has to do with peptide has something to do with amino acids or proteins. Now I've got 4 different examples of different amino acids up here. This is just a general structure of it. And if you notice, I'm like, so there are just 20 different amino acids. That's it. Just 20 amino acids. They all have the basic structural shape. They all have 1 carbon in the middle. And how many things can carbon bond to? 4. So I have to have 4 lines coming off of it. Off one of the sides off the carbon, it will have something known as an acid group. And so if you notice, here's the acid group, here's the acid group, here's the acid group. It's the exact same acid group on every single amino acid. On one of the other things that is bonded to a carbon, it has this amine group, this N with the 2 H's. And if you notice, on every other amino acid, all 20 amino acids have that exact same amine group. The third thing bonded to that central carbon is 1 single hydrogen. That's all it is. 1 single little hydrogen. And they all have it. So what's the only difference between all of the amino acids? It's this third thing at the top. We call it an R group. And I looked it up, and did I write it down? Oh, there's different things. I'm like, some people call the R for the residue group, some call it the radical group, and some call it the replace group. The R group, it's the only thing different between amino acids. And so I've got 4 different examples of the 20 different amino acids. They're structurally the same. That's all the brown part. The only thing different is what's attached to that 4th carbon. Glycine just has 1 single hydrogen. It's the easiest of all the amino acids. Others have more complex structures that hang out on the top. So amino acids are, quite easy to know because all you have to know to identify them is just what does that R group look like. And you're going to have to identify all 20 amino acids by the R group. Just kidding.
Can you give us
I did make one of my college bio kids or students do that one year. They did pretty well on it. It's actually not that bad. I mean, some of them are easy. Just a single each. Now, enzymes. We're still on proteins. Enzymes are proteins. So anytime we talk about an enzyme is an example of a protein. Not all proteins are enzymes, but enzymes are proteins. So we have proteins all over our body doing lots and lots of different types of things. One of those things, it might be an enzyme. These are proteins that act as biological catalysts. They help regulate and they help increase the speed of chemical reactions. There are millions of chemical reactions happening in your cells every second. There's no way those chemical reactions can come fast enough for our bodies to survive without having enzymes help speed up these chemical reactions. Now, the way that they speed up chemical reactions, any type of chemical reaction needs some type of starter energy to get it going. That's called activation energy. So they need some energy for it to start. What an enzyme does, it lowers how much energy is needed to start the reaction. If you don't need as much energy to start the reaction, it's going to start and go faster and get it done. So it increases the speed of reactions. And yeah, there's millions of reactions per minute. My favorite example is my frog one that I added on there that came from a different book. You have reactants, you have products. You have to have some type of chemical reactions to take reactants and make products. You need some type of energy to get from one side to the other. You have to remember this is like the before the arrow, after the arrow. And so this is known as my activation energy barrier. These frogs need enough energy to be able to go over this barrier to become products. What the enzymes do is they lower that barrier. You don't need as much energy now to go from a reactant to product, and the frogs get over there faster. That's my favorite picture. Your book's demonstration is looking at, here are my two reactants. Eventually they're going to join together and become a product. And without an enzyme, you need this much energy to go from point A to point B. If you have an enzyme, that little hurdle is a whole lot less, and it's going to happen a whole lot faster. I just like my frogs jumping over the thing. We have 11 minutes left. I'm like, our next part is getting into DNA. I don't want only 11 minutes to talk about DNA. So I'm going to have you guys work on your review sheets for 11 minutes. So pull out the review sheets that I handed out last time.